talk about dilations. Dilations are a change in size of a shape. So the notation is S of something, and it's really talking about size change. It's why we say like S of 2 or whatever. It's size change. We're going to talk about if it preserves orientation and if it's isometric or staying rigid. But we're going to look at some examples first before we go over that. Center of dilation is the point from where we are dilating. And for us, we're always going to do that over the origin. Scale factor, ooh, let me spell origin correctly. And remember the origin is 0.00. Scale factor is how much we are multiplying the length by. We're really looking at length there in a dilation. That scale factor is important. And again, dilation notation is always like S of something. I can just say K. If it would be S of 3, 3 is the scale factor. Okay, so we're going to do some examples and we're going to come back and talk about, does it preserve orientation? Is it isometric or rigid? So if we look right here, we've got a shape. And let's just label these points. We're going to call this A. We're going to call this B. We're going to call this C. Okay, so those are our points right there. And we are going to perform a dilation. We're going to increase this by a factor of 2. See if it all shows up on here. So if we're doing a scale factor first, we need to say what point we're doing it by. We're going to apply it to this, and we're going to apply. And we have dilated this by a factor of 2 from the center of dilation being 0, 0. Let's just double check this. So here is, I'm going to do a dilation. I'm going to choose right here as my center. I'm going to choose this as my object, and I'm going to apply. There we go. Now, this is a dilation of a factor of 2. So we are going to label the points of each of the vertices of my new triangle, just so we can see what these are. So this right here is my A prime. Then we're going to do this one over here. That's going to be B prime. And finally, we're going to do this one down here. This is my C prime. I'm just going to move this slightly because I didn't realize it wasn't right on there. And then we can just move this point right there. There we go. Okay, so we're just going to talk about each of these points. Right here, A is at 1, 2. And up here, A prime is at 2, 4. So we have, if you look at this, it's like we multiplied 1 times 2 and got 2, and 2 times 2 and got 4. It has doubled, the point value has doubled in size. Another way to look at it is if we look right at C, it's kind of easier to see the length. C is, we went over 2, up 0. So, you know, the distance from the origin is just 2. Where if we look at C prime, it is 4, 0. We went over 4 up 0 to get to that point. If we look at this, my orientation A, B, C is the same, but as you can see, it is not the same size. So isometric did not preserve. So does it preserve orientation? Yes. Is it isometric? No, it's larger or smaller. The length and area have changed. So we're just going to look at a couple of things with this. We're going to look at the distance right here from the origin. So if I was to make a segment right here from A, I went up 2 over 1. But if I was going to make a segment from the origin to A prime, I went up 4 over 2. We can look at that from C as well. We went over 2 up 0. We went over 4 up 0. It's increased. It's doubled the distance from that origin. So we can see that as well. If we look between A and B, I can count that that's 2 units right there, that length. If we look between A prime and B prime, we can go 1, 2, 3, 4. This is 4 units long right there. It's doubled in size. Okay, so that's really all about dilations, is showing that the distance from the origin changes, and also the lengths of the sides change, and where the points goes change. So this is just double the size. Now I could make another dilation, or I could change this one to have it be 0.5. And if we look right there, that's half the size of this one. Instead of C being at 2, 0, it's right there, that point right there. This point is C prime, but it is 1, 0. It is half as big. It has half the distance for it. So those are just some examples of different dilations, and that dilation goes through here. So I just want to talk about this real quick. So if I wanted to dilate something by 3, for example, and I had 2, 4, all I'm doing to this is I'm going 2 times 3, which is 6, 4 times 3, which is 12. That is a size dilation, a size change of 3. So whatever it says, if it says size 2, and we've got, let's say, these points, 1, 0, negative 2, 2, 3, 4. If I do a size 2 dilation, I am going to get 2, 0, negative 4, because the negative doesn't change, because I'm just multiplying it by 2, 4. 3 times 2 gives me 6, and 2 times 4 gives me 8. So that is how I'm performing dilations to get my new points, and then I could plot these 3 points and plot these 3 points and show my dilation.